I have one question. So what is MCS in terms of biological time?
Sure. That's a tricky one. In a lot of cases, how to convert MCS to real time. In a lot of cases, it actually doesn't matter a whole lot. If you're doing, say, cell proliferation, you would probably want enough Monte Carlo steps per second so that as you tell the cell to grow, it's actually keeping up with what it's supposed to be doing. If you tell the cell to grow to double volume, for instance, and say, well, one MCS is 1 second, well, cell doesn't actually grow that fast. So what you would do in the case of growing cells is you might say, how many Monte Carlos does it take to actually get it to grow so that it's never too much smaller than it's supposed to be? And then go and look, well, what's the doubling time for this cell type? You know, it's 12 hours. Well, and now I know it takes 150 Monte Carlo steps to get that cell to grow properly in CompuCell. And that's supposed to represent 12 hours biological time. So now you have your conversion. Other ones to use are things like if you're doing chemotaxis, if your Monte Carlo step represents too much time, you're trying to make the cell move too fast and the cell will fall apart. You have to put too big of a force to get it to, it's supposed to chemotax 1 micron a minute. And in order to get that to do it in your model, it takes too big of a force and your cell falls apart. So you have to use smaller forces and more Monte Carlo steps to get it to move 1 pixel. And that is the speed limit. And that's how you would set your Monte Carlo to real-time conversion. Like I said at the beginning, a lot of times it actually does not matter a whole lot. If a Monte Carlo step is 1 minute or 2 minutes, might not make any difference at all. It will make a difference if you think a Monte Carlo step is 1 second and it really should be 1 month. Cancer models, your Monte Carlo steps typically pretty big because tumors tend to grow pretty slow. And you don't want to be doing, 1 second Monte Carlo steps because it'll take you too many steps to simulate 2 years or 6 years or however long you think it takes for a tumor to grow.
Thank you.
I think you can make them as small as you want, but you can't make them too big. Basically, it's like any other computation where if things change too much during one step, you have numerical issues.
Yeah.
And so you have to figure out what the fastest process is in the simulation. And that fastest process will define the time step that you have to use. You can, if the fastest processes are not cell movement, you can substep to make basically subdivide that intrinsic Monte Carlo step into subunits. There's a very awkwardly named quantity called flip to dim ratio, which really makes no sense at all as a name if you don't have the history, which allows you to say, I want to call the diffusion solvers or the antimony solvers 5 times every Monte Carlo step instead of every Monte Carlo step. And so you can do some fine grained tuning that way, although it has to be done by hand.
Yeah. And on the other end of the scale is if your time step is much too small, a Monte Carlo step is a millisecond. The problem is you're trying to model a slow process. You have way too many steps and it's just going to be too slow. So on the low end, you can't break the model. And on the high end, you don't want to spend a whole bunch of time calculating these real fine steps that don't actually do anything of use. You have to find a happy medium. And as I said earlier, usually that happy medium is a fairly broad range. It's not a real sharp minima. It tends to be it gets better, it gets better, it gets better, and then it goes flat. And you can use anything in the flat and it works just fine. You just don't want to be on this slope where as I change my step size, the model is behaving differently.
Right.
As long as the model is, if you make small changes in your Monte Carlo step size and the model behaves the same way, then you're reasonably confident that your model is not sensitive to your step size.
I mean, it does depend. And for example, in the liver simulations where we were modeling blood flow and capillaries explicitly. Blood flow in capillaries is very, very fast.
Yeah.
And if you want to model the changes due to pulsatile availability of a chemical in the blood, you wind up having Monte Carlo steps of 100th of a second.
Yep.
And that makes
Yeah,
the
that's right.
simulations very, very expensive.
Yeah.
If you're doing simulations where you're having immune cells move, some of the leukocytes move very quickly. Macrophages crawl quite rapidly. And so then your Monte Carlo step might be a few seconds to 15 seconds. For most developmental simulations, a Monte Carlo step can be a minute or 2 minutes, represent a minute or 2 minutes. And there definitely are simulations we do, for example, diabetic retinopathy, where things happen very slowly, and the typical time step we'll use is 15 minutes or 20 minutes. So it's really determined by the timescales of the biology that you're trying to represent.
Yeah. So when in doubt, say 1 minute, 1 Monte Carlo, and write that in your parameter file. And then as you work through the process of building your model, you'll find out that that number just doesn't work. It doesn't match your diffusion coefficients or your growth rates or something else. And that's fine. And you in your parameter file, you change it. So yeah, Monte Carlo step is now 6 minutes or whatever it should be. And that's fine. But at least if you have a number written down, you know where you're going.
Right. One thing you have to remember is that if you have probabilities of transitions, you have to use the Poisson rule when you change the step size. It's not linear in the step size. But beyond that, typically we are careful about that these days. We'll have that equivalence, say 1 Monte Carlo step equals X amount of real time. And then when we change that, we have all the parameters written so that they automatically rescale appropriately when we do that. Right. But again, that's the kind of thing which in principle would be very nice to have automated, but in fact, every simulation is so different in terms of the way it handles it. It's very hard to think of a way of doing that automatically. So I just wanted to close up, and we're having a good discussion here. I don't want to cut it off. Tomorrow we have the hackathon. I hope we'll see a lot of you there. We'll start officially at 10 a.m. I'll try to open the Zoom at 9:30. Please, if you have a name for your hackathon team, please put it into the Google Doc so that I can have it for this to set up breakout rooms. I will ask people to go over one more time very quickly their projects so that people who want to join the hackathon who don't have a project yet can decide who they want to join, at least temporarily. If people decide they want to merge projects because there are two projects that are very similar, I don't see too many like that, but it's possible. Let me know. Then from 11 to 1, we'll have a work session. We'll have as many of our assistants and as possible available. My guess is there'll be more people to help out Saturday than Sunday, just because everybody's getting tired. And I encourage you, if you haven't started yet on your project, to start thinking about some of the material that I provided earlier today. We'll do a very quick half-hour check-in. You don't have to do the check-in, but we'll be available for a check-in around 1 p.m. And then actually I have a self-inconsistent timing here. Between 1 and 3, there were some requests for some informal presentations. I don't want to distract from the hackathon too much, but we'll use the main room. TJ will show how to do advanced applications, how to call CompuCell as a Python library element. So to use that, people have asked for that. He might talk a little bit about job scheduling as well, his Slurm script. Giuliano will talk about how to build Nanohub applications. We've been using the raw CompuCell Nanohub mostly, but TJ showed a Nanohub demo of the COVID model that was a packaged Nanohub app. So if you write a simulation in CompuCell and you want to have that packaged as a freestanding application, Juliana will show you how to do that. And then Julio has agreed. There were a lot of requests to show how to do this subcellular chemical concentrations moving around in the cell. And he has this nice quantum polarity and Drosophila demo, maybe also a PIP23 demo that he could show briefly. These won't be polished necessarily. They may not demonstrations, but there'll be an opportunity for people to find out a little bit more. I hope it doesn't distract too much from people working on their own projects. We will record them and make them available. So if you miss them, you can always go back and watch them another time. But these are topics that we didn't get to during the main course. And I'd like people to have the opportunity to see that material if they want to. I would, again, encourage people to focus on their hackathon projects. If you are part of the hackathon, you don't have a team, please look over the list of possibilities. I know Priyam, who has been an instructor in previous classes, agreed to come and help us out tomorrow morning a little bit. She's an expert in using links and doing epithelial reorganization, so that should be very helpful in doing compartmental cells as well. So, for example, for the lateral line project, I think she has a lot of relevant expertise. So that would be our schedule for tomorrow. Are there any more questions before we break? I know it's been a very long week. I appreciate those of you who've stuck it out all the way. I really appreciate the ideas that people have for projects, and I hope we can make those work. I'm quite excited by the variety of projects that people have proposed. So are there any final questions? We're already over by 15 minutes, and I know for our European colleagues, it's very late.
I have one doubt regarding the hackathon. So the past day reports means this this format that you have sent that report, or what else, like that one or anything else?
No, it's not that formal. But at the end of the day, I would like to go through all the teams and have each team report in front of everybody what they did. That could be a slide or two. It could be showing a simulation. It could be saying you got stuck. It could be a document that shows what the conceptual model is. Any of these things. But we have a lot of expertise and a lot of ideas. And so I think it's worth spending 45 minutes learning from each other and seeing what worked and what didn't. So the goal of this first day report is not to have a formal report. It's not that you have to hand in a 20-page PLOS computational biology paper. It's more to have an opportunity for people to present, learn from each other, discuss problems, and help each other out. Okay.
Okay, thank you.
I actually have a specific question. Sorry, I won't be able to participate in the hackathon for the weekend, but I just want to ask this question. So is there any ways, because I know like the volume flex can make the cells freeze, but is there any way to set up like a material properties to the cells or to like the substrate materials? Because what I want to do the simulation is like make my cell adhere to a substrate which have different Young's modulus, and I don't want to apply the forces directly to the cells, but I want to apply the forces on the substrate and let the substrate stretch the cells.
Okay, so there are two possible ways of doing that. One of them would be to use a finite element package like FEBio,
Okay.
or one of the Python libraries that models the solid material, and then couple the solid material using the explicit force that Giuliano showed in the second second day between the solids model and CompuCell using the Python interface. That may be the most efficient way to do it. If you want to do it entirely inside of CompuCell, it's very possible to do that. You can divide your solid material into small blobs using the cells, generalized cells. You cross-link those blobs using links, and the spring constant of the link is the Young's modulus of your material. And then
Oh,
you
okay.
can couple, your cells to the subcellular, extracellular material that way. The only disadvantage of doing it that way is, one, because you're on the lattice, there's a little bit of nonlinearity in the mechanical response. If the forces are very small, things get stuck. So there's a binding friction, a starting friction term. And for larger forces, it's fine, but for small forces, that can be an issue. And you have to use a fairly small lattice constant, because you need to have the size of your blobs of material in the solid be multiple pixels and still much smaller than the cell. But you definitely can do that, and people have done that. Last year, there were people who built models of extracellular elastic material, and then put cells on top of them, and then pulled on the elastic material and had that pull on the cell. So that's definitely a possible thing to do.
Okay, I see. Thank you. So so you're saying there is a way that to implement FE-Bio into the CC CompuCell 3D?
No, I'm not saying anybody's
Oh.
ever done it. I'm saying it's possible to do it.
Okay.
There are Python libraries that do finite element simulations. If
Okay.
TJ, are you still on the call? What is the one we were just talking about the other day?
Now I'm trying to think of it, and I'm also blanking.
Sorry, can you repeat that? I was distracted for a second.
So there are a number of solids and fluids modeling packages in Python.
Yes.
And you can use any of those inside of CompuCell if you want to implement a solid material or a liquid using those. But then you're on your own, in the sense that you have to then write a description of how the objects created in those models exert forces and have forces exerted on them by CompuCell cells. It's not intrinsically difficult to do, but it does take some thought to make it work efficiently. But there's certainly no reason you can't do it. A long time ago, we had a Phoenix integration part, but the problem with Phoenix was it doesn't run on Windows, so we didn't pursue it.
Actually,
Okay.
today I was very impressed by the 3 sort of cell version of creating these for the apical constriction, and that together with what we learned yesterday about single cell migration, it's made me rethink how I might incorporate these ideas into a primordium which has a subset of cells that undergo apical constriction and a subset that remain more mesenchymal for collective migration. And that actually might be a good way to do it, which would not require me to go outside and actually take full advantage of many of the things we learned in a couple of days.
Yeah, I think, I mean, the simulations you showed, the ones you showed it with NetLogo,
Yeah.
those you should be able to replicate relatively quite straightforwardly.
Yeah, no,
If you want to include more mechanical properties, again, the issue that comes up always when you do detailed mechanics is that you have to have very fine pixel size. And so then the simulations get to be quite large in terms of voxel by voxel, because you need to have a high spatial resolution. But it works quite well. In the past, this year we didn't have time to do it. I've written simulations where you build essentially a square of a material, cross-link of blobs, cross-linked by links.
Yeah.
And then you pull on it and measure the stress-strain relation. And then you can adjust if you use crossed links, you can have Poisson ratios, different Poisson ratios, and this kind of thing. No, you're never going to be as good a solver as Abacus is, because they've spent billions of dollars developing code to do these things in great detail. On the other hand, it's very convenient to be able to do everything within one package rather than to have to go outside of it. And so you have to decide what the trade-offs are for your particular application.
No, considering I already got something useful out of something as simple as NetLogo, I think this is already going to allow me to do a lot of very interesting things. And so, yeah, I'm actually much more optimistic. In fact, we had this little discussion about how reasonable it is to elongate the cell. And actually, you raised a very good issue, because I think that I was too focused on getting everything done simply by cell adhesion. But in our cells that undergo apical constriction, they have actually been epithelialized, means their shape has become elongated. They have acquired that polarity. So it's actually a bonus to include that as a feature of how the cells change. And conversely, I might use that feature to define what a more mesenchymal cell is by changing that in the opposite direction. And it turns out the microtubules change their orientation in migratory cells versus constricting cells. So all that actually becomes biologically perfectly reasonable.
Right. Well, if you look at the simulation that Gilberto did, he didn't show the 3D version of the cell crawling this year, but that's a very mesenchymal cell.
Yes.
He's modeling essentially a keratocyte.
So I'm thinking of actually incorporating both ideas now.
Right. And if you look at Giulio's simulations of segmentation or of kidney polycystic kidney disease, in that case, he has very strongly polarized cells that are very elongated. And he uses this method of defining apical basal domains and then defining essentially something that represents the extension of the cell by the microtubules. And that works quite well. Again, as you make the cells more detailed, the lattice gets more fine grained, and therefore the computation gets more expensive. But once you have a simulation that does what you want, if the simulation takes a long time, it's no problem. You throw it in the cluster and you wait. When you're fine tuning it and trying to get the parameters working, then having a slow simulation is more of an issue.
Yeah. So actually, I wanted to go back and read and look at the model where it was mentioned that the somatogenesis happens as a consequence of mechanics rather than how it's normally described. So which paper is that? I tried to look it up. There is one paper, but it seems just superficially when I looked at it, it was more like the traditional notch oscillation clock and wave front. Is there a different one which describes it much more purely on the basis of mechanics?
So Giulio has a paper in Science that does it. The modeling is all in the supplemental materials, so you have to look in the supplemental materials.
Okay, I'll look that up. Okay.
And then there's a recent paper with Giulio and Priam on mechanical instabilities in epithelial layers that does some of that related to somatogenesis. And then Priam has some work that she did in her PhD thesis, which you can find online, that was not published, where she did three-dimensional reorganization of tissues. So most of the simulations that I've just talked about are 2D simulations, but she did a full 3D model trying to do somatogenesis. And she graduated before that all got nailed down, but it is in her thesis, and it's well worth looking at.
Thanks.
Somebody says it's too bad that the last two sessions were short and a little bit accelerated. I guess that I'm sorry we don't have more time together, but you've given us a lot of your time over the past 5 days. You've given us 30 hours of your time. So we didn't want to take too much, but please do feel free to reach out and ask for more details. There is documentation of most of these things in the online manuals. Sometimes the manuals are not so clear. And if you find that the manuals are not clear, please do put a pull request into our Reddit and say, hey, page such and such of the manual says this and I don't understand it. Because the best way that we have to go back and fix things is to have people tell us that we need to improve. If you tell us where we need to do better, we try. Okay. Anything else we want to go over now? Otherwise, I will see you. I'll see you, many of you, I hope, tomorrow morning.